So hello everyone again. In this lecture, I would like to talk about sort of a high-level overview of this one component of the system, OOPS, the object-oriented prediction system that we've already talked about today, and a bit about how it connects to the other components of the system that you might have noticed when you were cloning your FV3 bundles in the practical today. So just a recap of what you've already seen in Yannick's lecture. So OOPS, the object-oriented prediction system, is sort of an abstract layer where you can find the what we call generic applications, for example, a 3D var, a 4D var, an EDA, an ENKF, an H of X, which is basically just a forecast, a model forecast combined with a computation of the model equivalent of observations, so the observation operator. So you could use that application, for example, for the diagnostics purposes. So all those applications and all the data simulation algorithms live inside the OOPS repository. And the way they're written is they use this, the abstract interfaces that are also defined in OOPS. For example, state and model and covariance, ops operator, etc. The abstract interfaces, not the concrete implementations, what you can find in OOPS. And if you look at those generic applications, the way they're written, it's you can think of that in some way as a reading or writing an data simulation algorithm in a paper. It's not exactly, but you can sort of see how the equations and the successions of steps that you need to do to compute a 3D var analysis increment or a 4D var analysis increment or an ENKF. So this OOPS layer, there are no details about what kind of model you run in or what kind of observations you're using. It's operating in this abstract interface level. Then once we have those, if you actually want to run a 3D var or 4D var, you would have to have implementations of those abstract interfaces. So an example of what you saw in the bundle, you saw if you looked inside your FV3 bundle repository directory, then you probably noticed that there is OOPS and then there is an FV3 JEDI. So the FV3 JEDI contains implementations of these abstract interfaces that are relevant to the FV3 model. So if you look inside that repository, you can find how the state is implemented. In this case, it would be storing, the relevant variables on the cubed sphere grid. How the model is implemented would be calling the GEOS or GFS or the simplified version of FV3. FV3 has several options, but basically that's where the implementations of the model related interfaces live. So another, not in this FV3 bundle, but the other groups have developed interfaces to different models. So you can have an interface to MOM6 Auschwitz model, you can have an interface to AMPAS or WRF, a LEN model, etc. And those would also implement the interfaces that are relevant to the sort of model side of data simulation. You might have also noticed that there is a SABRE repository, the System Agnostic Background Error Representation, and that's sort of generic implementations of background error covariances. And in this case, they're generic in the sense that they could be shared or used by different models. So, for example, a lot of models use the bump covariances that you'll hear more about later this week. And basically, FV3 could use them, MOM6 could use them, AMPAS model can use them, and any other model can use them. They could be shared. Another two repositories that you probably saw in the bundle are YAML repositories. So that's the interface for observation data access, and the UFO that has been mentioned several times today already, the unified forward operators repository. So that's where all the observation operators live. And again, different models can share this observation operator. So if we write an interface to CRTM, let's say, we just write it once and then FE3 could use it, or MPass can use it, or in the future, a coupled model, let's say FE3 and MOM6 could use that interface as well. Okay. And this sort of generality or this ability to use data assimilation algorithms from OOPS and say background error covariances from SABRE and observations from YODI and UFO means that you can switch the implementations from say FE3 on the previous slide to the MOM6, and you can still run the OOPS 3 var with the observation operators from UFO and YODA. And it's pretty seamless once you have the development in those general repositories, and also once you have implemented the interfaces that are defined in OOPS. Okay, so let's talk a bit more about OOPS and this sort of abstract layer, and then towards the end of the lecture, I'll show you how the implementations are connected to this abstract layer. So as Yannick mentioned today already, or talked about today already, the idea is that we're trying to define this second layer on the slide, the previous slide, the interface layer of sort of building blocks using which we could write the data assimilation algorithms. And the idea behind it's pretty simple. You know, all data assimilation methods require more or less the same number of entities. It's you know, you could kind of see it just by reading data assimilation papers. And for future developments, these entities should be easily reusable. And so those entities or building blocks are this abstract interface classes that basically define the system. And I'd like to give you just a couple of examples of what those interface classes are. We'll go more into details on the interface classes on the observation side, I think tomorrow, and on the model side the day after that. But I'll just give you an idea of what they are and what operations are defined on them. So if we just go to and ask ourselves a question on what is data assimilation, we're all trying to find the best estimate of the state of the system, given the background, the previous estimate, and the recent observations. And for deterministic data assimilation, we could use variational assimilation and minimize the cost function, or we could use a Kalman filter and find the analysis increment by using Kalman filter equations. So the first example of the interface, an abstract interface class is a class that's called state in OOPS. And it's a model, it's a state in a model space. If we just look at formulas, you can probably easily identify what it is for different algorithm, right? So examples of state are your background is a state. The analysis, the result of data assimilation, is also a state. And if you run forecast in time, then each of your x'th is also, the forecast state is also of this type or class state. So as we were talking about, when we define the classes and when we define the interface classes, the most important thing to define is what are the operations that we can do with those things? What are the methods on the class, right? From writing a paper point of view or from the OOPS point of view, it doesn't matter how you store your state from the programming point of view. It doesn't matter what grid it's on. All that matters is that you are able to perform certain operations on this class. And for state, those operations could be, for example, input or output. We should be able for the assimilation to move the state forward in time. We should be able to copy states or assign states. And again, from data assimilation or from OOPS point of view, there's no need to know how these operations are performed in the implementations, how this is done in FV3 or MPAS or MOM6. From OOPS point of view, we just want to know that these operations are defined and we can perform them. Another example of interface class, sort of on this model side of things, is an increment class. And an increment is sort of a difference between the two states, if you wish. So an analysis increment is of type or of class increment. An ensemble perturbation, if you do an ensemble data assimilation, is also of the same type. And it's important to understand the difference between what the state and increment is, because on some level, if you're just looking at the equations, you think, they're both vectors in the same space, right? The difference between space and increment is what we can do with those. So what operations are allowed, we are allowing to do, and what are the methods that we define in this class. So where in state we could read it and run it forward in time with a nonlinear model. For the increment, what we can do is we can do some basic linear algebra operators that are probably going to be useful for, say, variational or even Kalman filter DA. We could run it, revolve it forward in time with a tangent linear model or backwards with an adjoint. We can compute it as difference between two states. So if we subtract one state from the other, we get an increment on the output. And if we add an increment to a state, then we get a state. So it's there's this distinction in what the interface of this class is. So state and increment are a couple of interfaces. Then observation side, there's sort of two, in some sense, similar interfaces that are in the obs world. We have a class that's called observations. So observations is sort of a vector in the observation space. It could be observation values, so YO in this formula, or it could be a result of observation operators. So if we apply observation operator to the background, the result of that is observations. The input argument of that is the state, and on the output we get the observations. And what we can do with obs is we can input output, we can assign it the value of h of x or h of xb plus delta x, that this input again is a state. We could copy, assign, and again, from OOPS or DA point of view, there's no need to know how you read in those observations, which files they were stored in. All we need to know is we can read in observations and we can assign h of x to something. A counterpart, so observations, you can think of that as something that's similar to state, but in the up space. And then we have a class that's called departures, which is something that's similar to the increment, but again, that's in up space. So it could be a difference, a departure, difference between obs and the h of x background. It could be the tangent linear observation operator that's applied to the increment in the model space. It could be the ensemble of perturbations in the up space if you're working on the ensemble methods. And again, the interface for departures is different from the interface for the observations, because unlike observations for departures, you can apply tangent linear or adjoint observation operator. You can do some linear algebra operations that might be prohibited to do on the observations, and etc. So these are just 4 examples of interface classes that you might find in OOPS and that are used when we write, or we have already written, the data assimilation algorithms or the applications. And just a couple more examples of the interface classes. So I titled it operators. It's the operators served in a math sense, not in C++ operators. So it's two interface classes. One, which is a model. So that's the forecast model, which you can forecast or move the state forward in time, change the state using the forecast model. And another one is the observation operator. So that's, we take the state on input and we get its equivalent in the observation space, the observation class on the output. Okay, one thing I wanted to emphasize that there's the important concept of the separation of concerns. So, and it goes both ways. So we've just talked about that OOPS is written in a way that is independent of the underlying model. It's independent of the physical system. It sort of operates this on this abstract interface level. But another way of the separation of concern is that not only OOPS doesn't know about how those abstract classes are implemented, we can also say that the implementations don't know about what high-level algorithm is run. So the implementations are implementing these interfaces, like we talked about state. An implementation of a state interface should be able to read a state, write the state out, propagate it with a model. What else could it do? Do some copies, right? It doesn't know how those, at the level where the implementations are written, they don't know how this functionality is going to be used. I might be running just a model forecast, or I might be running 4D in var, or I might be running something else. And there's this separation of concerns between those sort of two levels of the high level algorithm and the implementation of the interfaces. One thing that it means, the biggest thing that it means, is that it's best to avoid using global variables in the implementations level, because that could get messy very quickly. And just a note on interfaces, I mean, they're, as Yannick said, pretty much settled at this point. But when they were developing it, the idea is that these interfaces, they must be general enough so that we can use them in different cases. And they also must be detailed enough so they are able to actually perform all the actions that we need. So there's this balance between how detailed you want your interface to be. And I had an experience of adding a new algorithm to, or helping add a new algorithm to OOPS, which was a completely different algorithm from what OOPS was designed to do. So we were adding LTKF, whereas everything that OOPS did before was the variational algorithm. And we only had to add a few new interfaces. Like, we did have to add a couple of methods and a class, but I'd say the interfaces were designed pretty well to begin with, because we didn't have to add a ton. Right, so just to illustrate the separation of concerns, so this is the picture that you've seen before. We have this abstract layer, and we have the implementations, and the top level, so the generic applications operate the interface layer and don't know about how those interfaces are implemented. But also the implementations just implement the interfaces and don't know anything about this generic application level. Okay, a little bit about, if you're going to be browsing the OOPS code, just a little map of what you can find where. So inside OOPS directory, you'll find source, and then there's another OOPS directory. And then there's an interface directory, and that's where all the interface classes are defined. So those are those building blocks, the state, increment, model, etc. that we looked at on the previous slides. And those are the classes that need to be implemented to be able to actually run the OOPS applications. There are a few other directories. So in the assimilation, you'd be able to find some data assimilation classes. That's where you will see cost functions, minimizers, and LTKF solver, things like that. The generic directory contains some implementations that, again, can be shared by different models. So that's where you could find things like pseudomodel. Pseudomodel is not propagated model with a actual physical model, but instead it's trying to read the states. And the diagonal observation errors also live there. And then there are a couple of sort of utility directories that contain utility classes. And then another directory I'd like to talk about now is the directory that's called runs. And that's where all the generic applications live. So if you look inside that directory, you'll see what OOPS can do. So the examples are, there's a variational. So we actually don't have a separate 3D var or 4D var application. It's called variational. And then there's the HFX application, and there are many others that you can take a look at. Okay, and now at the end, I would like to give you an example, or at least some sense of how those generic applications are connected with actual implementations. So we'll do this at the example of HFX application, and that's something that you will be running in this afternoon tutorial. The HFX application lives in runs directory. It's called HFX. And what it does, in the most general case, is it runs the model forecast and computes HFX for the observations that you specified with the observation operators that you specified. It's possible to run it with a pseudo model, or so it just reads the states instead of actually running the model. I think it's probably possible to run it with just one state. So you just sort of do a 3D HFX instead of a 4D one. And it has an option to generate observations. So you can compute HFX, perturb it a little bit, and save it as an observation value. And we use it in tests, but it could also be useful for OSSI. Okay, so this HFX application that you will see in the runs directory, that's still a generic application. So if you look at it, you'll see this the templated classic angle brackets parameters in the application. So at this point, this is still generic. To be able to run it with some implementation, we create small executables or small main programs in C++ for each needed combination of model and application. So let's talk a bit about how the FV3 JEDI HFX, the actual FV3 JEDI HFX application looks like. So this lives inside FV3 JEDI repository. You can go there and have a look at it. I have extracted 3 lines of it, but the main function, I think it might be 1 or 2 lines longer, but that's basically the main thing that you will see inside this, the instantiation of the OOPS application. So let's just go line by line. The first line, there's OOPS, double colon is sort of a C++ namespace things. You can just think about this as a class run that comes from OOPS. And this first line, this is sort of a technical setup. It takes the command line arguments on input, and all OOPS applications have one argument, and that's the YAML configuration file that you will be looking at this afternoon and also through the week. And I'll show you a short example in a couple of slides. So this OOPS run line does some technical setup. So it reads the configuration, It starts MPI if needed, it starts some log streams, etc. Then the next line is really where the magic happens. So we have an HFX, we have an HFX class, again, coming from OOPS. And then in the angle brackets after that, that's the sort of template parameters. And so this is the traits that Yannick mentioned, and I'm going to talk a little more in the next slide about. This is what you want this HFX application, this particular one, to be instantiated with. You basically at this point saying, okay, I want the HFX, that generic application from the top row of our diagram, and I want to use it with these implementations from FE3 and from UFO. And then the last line just executes the application. So it's basically, that's where the second line is where we kind of replace or put in the actual implementation in place of where OOPS was saying, okay, I'm just going to propagate state forward with modal. So at this point, at the second line, we know that I'm going to propagate the FE3 state with the FE3 modal. And then the execute line basically just executes the code that HFX is meant to execute. Okay, so just a repetition of the second line from the previous slide. So we have HFX application, and we pass it FE3 JEDI traits and then the UFO traits. What we pass it is template parameters are in this angle brackets. So here's how this FE3 JEDI traits look like. So it's a structure, which is something that's simpler. It's kind of like a derived type or just a combo in this case of things that are put in between this these brackets. And in there, you will see a bunch of lines looking like this. And those typed Fs, as Yannick said, are basically aliases for the type. So what it says is, in OOPS, wherever I'm going to see state as an interface class, I would like to use FE3 JEDI state. And that's a class that's defined inside FE3 JEDI repository. And wherever I'm going to see the increment, I'm going to use this class. And it's important that those classes actually implement the interfaces, otherwise your code doesn't compile. So it's the FE3 JEDI state would have methods to read, to write. The increment would have the ability to add increments, etc., etc. So now if I wanted to run the HFX with an MPass model, I would have also that 3, 4, 5 line short executable, or sorry, the main program in C++. And one big change that happens there is I create an HFX application, but I say, I'm going to pass there an MPass traits. I'm going to say my implementation of this model of related class is going to come from this MPass traits. And if we look at that, then again, it says state is going to be this class that's defined in MPass, and it's called state MPass. And it's also going to be implementing the abstract interface that's defined in OOPS. So you'll also be able to read the state, propagate it forward in time with a model, et cetera, et cetera. So now if we go back and look at this two instantiations of HFX with FE3 JEDI on the left and with MPass on the right, then you probably notice that there's a second parameter after the FE3 JEDI and MPass traits, and it's called UFO obs traits. And both FE3 JEDI and MPass use the same obs trait. So if we look at that, that lives in this unified forward operator repository, which contains those generic implementations of observation operators. And you could have a look at it. It contains classes from YODA and UFO. And the idea is that since this is implemented once and for all inside YODA and UFO, there's less to implement for sort of model traits. So you only implement those model related things in the model traits, and then the observation operators are shared by using this UFO trait. Okay, so that's kind of an overview of how on the code level the OOPS generic applications and the implementations are connected. If we go back and just look at HFX application, the generic application that's written inside OOPS, it's approximately 50 lines of code. I mean, it's because we have the interface classes, but we also have some helper classes inside OOPS, so that helps to bring down the number of lines for something as complicated as running a forecast model and computing observation operators for various observations. But if you look at it, you'll see there will be a bunch of setup. First, I removed all C++ code and just left the comments. So 2 slashes is how the C++ one-line comments start. So there's a bunch of setups that we'll discuss in a bit. And then the code is run the observer, which includes running the model and computing HFX and running QC filters if you specified any. And then there is an optional step of perturbing HFX if needed. This is typically just for either testing purposes or for OSSI. And then you can save the result of HFX. And typically it's saved as HFX in the file. But if you specify an option in your configuration, you can make it save as the observations again for observance simulation system experiments. Okay, and the last thing I wanted to talk about is this YAML configuration files, which is that single parameter to the OOPS executable or to your JEDI executable when you run an application, and how they're used. You'll hear more about them tomorrow, I think, and also you'll read some more about them in the tutorials. But I just wanted to give you an idea of how this setup, that the first few lines of setup in the code correspond with what you see in the configuration file. Okay, so I'm just gonna leave the setup part on the left, the code or the comments from the code. And on the right, you see extracts from the configuration files. And just very briefly, you will see a key and then colon and then a value. And so when we set up the observation window, if you would look in the HFX code, you will see that we're reading what's called window begin from the YAML file or from configuration file. So in this case, it's set to this date, and then it would read the window length for how long do you want to simulate the observations. So then to set up geometry, it will all still be in the same one configuration file, but you will see a section that starts with the word geometry. And you could have, it depends on the model, what you would see in the section, but you could see, for example, the dimensions, vertical, horizontal, things like that. Then we have a part that sets up the model. And 3 dots that I'm putting here is just like there can be more, or it can be something. You would typically see what name of the model we're using. You could see there, I don't know, again, depends on the model time step, what the model variables are, etc. You would set up the initial state. So you would see words like initial conditions, condition, and then there could be a file name there, what to read, where to read from, or there could be which variables you want to read from that file, etc., etc. You'd also see a forecast length. So that's how long you want to run a forecast, because it allows you to, say, run the forecast for longer than you need to simulate observations if you want to. And then the last big section that you would see is setting up the observations. So you would see there are sections that look like this. They call it ops space. Those are typically prescribing which file to read observations from, which variables you want to simulate when you run HFX. What do you want to call this ops space? And then you would see sections like ops operator, what observation operator you want to run for this particular data. So in this case, we're running the one that's called vert-interp, which is short for vertical interpolation. So we just want to do vertical interpolation for aircraft data. And we'll talk more about observations tomorrow. That's all I have for today. If you have any questions, please go ahead.